Welcome friends. Let us discuss the first 10 questions of machine learning in my machine learning series of lectures. So this is from YourPedia, and most of the material I am be showing or material I have taken is from my own book, that's a machine learning book from YourPedia publishers. You can get the printed versions also. So this book I will be following. So the first question is, because of low bias and high variance, we get which model? High error model, perfectly fitting model, under fitting model, or over fitting model? What we are talking of, low bias. Low bias means bias error is low. So we have definitely taken some complex model so that our data is fitting well in the training set. That's why we are getting low bias. So once you will get low bias and you are getting high variance also, means now your data is so complex, your model, that it's not generalizing, it's not getting validated through other sets. That's why you are getting high variance. So basically what you have done, you have overfitted. D is the answer, overfitting. Because of low bias and high variance, we get overfitting model. Overfitting is the answer. Why? Variance is the generalization error we get across many training or validation sets. When we adopt a complex model to fit exactly in the training set, we get low bias, but the complex model is not able to generalize across different sets. This situation is called overfitting. Like you see here, this is the underfitting situation. You have got some data. Data was distributed like this. Now you are applying a very simple model, that is a linear model. So this line is not fitting. We want like this. Data is distributed like this, but we have fitted a single line. So what will happen? There will be a lot of error in the training set, and that will be called bias error. So here, since we have applied a very simple model, a single line, we are getting high bias error. And here you see, we have fitted our model to each and every data. So this shall be a very good situation. Here, bias will be very less. It may be 0 because there is no bias error. But the problem is now high variance will come. Why high variance will come? See, this is the ideal situation. We have fitted the data, but there are some outliers, the points which are lying outside. The points which are lying outside, they may be due to noise or they may be measurement errors. Those are also possible in real life situations. So that's why fitting to each and every point will create high variance, and that is overfitting error. If we will fit to each and every point, then this model will not be general, it will not be applicable across different data sets, and that's why it will give high variance error. So this is the good balance. It has generalized, it has taken the extract and generalized. There are some outliers, it has not tried to fit each and every point, because the point which are lying outside, they may be due to error, due to noise also. So this is the situation. When we fit too simple a model, our bias error is high, and you know bias error is high, though variance error may be low at that time. But when we fit very complex model, then bias error reduces but variance error increases. This is the overfitting zone and this is underfitting zone. Here we have fitted very simple model. As a result, underfitting has happened, bias error is high, variance error is low. But as we have started fitting complex models, bias error has come down here. You know, bias error has come down, but variance error has increased. So this is the point where we choose our models. Entire machine learning thing revolves around this bias variance dilemma. Entire thing. Everywhere we are trying to do the same thing. There we are trying to adjust bias and error. So now second question. In SVM, support vector machine, non-linear problem can be solved by transforming data from dimensional space into dimensional space. Okay. So whether it's high low or low high or low medium or medium high, what are we going to do? What happens in support vector machines? So now let us proceed. The answer is low high. So in SVM, non-linear problem can be solved by transforming data from low dimensional space into high dimensional space. Why? You see here, this is the support vector machine concept. Some data points are this side, some data points are that side, they are linearly separable. So support vector machine can be created with the margins, and that is separating the two classes. But what if we are getting data like this? Here no line is there which can separate. Actually we need to draw circle to separate these green points from blue points. We need a circle, line can't separate. So what we do, we apply a different concept. Whatever is not separable in a low dimension gets separated in high dimension because of the projections. See how this is happening? Add a dimension z, that was a two-dimensional data xy. Now we have added a dimension z is equal to x square plus y square and distributed the data again according to that in zx dimension. So now the data has come like this, and here we can draw a line. So support vector machine can now draw a line and classify the blue points from green points. And after classification, we will again project it to low dimension, and then you see this circle has come automatically. So simply support vector machine can calculate this line, and then we can project it back and get the classification thing. So that the example was that we have projected low dimensional data to high dimensional data, and there we have classified it and then projected back to low dimensions. Now third question, fraud detection, image classification, diagnostic and customer retention are applications in whether unsupervised learning or supervised learning or reinforcement learning or unsupervised learning. What is unsupervised learning? There is no supervisor. Data we are getting is not classified, data is not labeled. So the machine itself is labeling the data. First it will do clustering, it will take similar data, separate, and then it will do labeling. That machine will do itself, it will give its own labels. And in supervised learning, there is a supervisor who is telling this is this, this is this, this is this. And like that supervision it is doing, and we are getting labeled data. Reinforcement learning, we are actually working with the atmosphere mainly in game playing, or where one sequence, one action can't lead to the result. There are sequence of actions like chess game, sequence of moves leads. There reinforcement learning will be needed, where we are actually going to interact with the environment. And then unsupervised learning, regression. Unsupervised learning is used for clustering also and for regression also. So question is fraud detection, image classification. See, wherever image classification has come, it can't be unsupervised. Image classification is a supervised job, so naturally it will be supervised learning classification. That will be the right answer. It's supervised learning classification. Now the third question, which is the partition approach of grouping similar data with same size clusters? See here, same size clusters are being used to partition the data. So whether it's KNN, K nearest neighbor, or K means clustering, or artificial neural networks, or HAC, which one it is? So here you can see that it's K means clustering, because similar size data. Similar size data means K means clustering. What is K means clustering? It's an unsupervised learning algorithm which groups the unlabeled data set into different clusters. Here K defines the number of predefined clusters, in how many clusters we will divide, that need to be created in the process. As if K is equal to 2, there will be 2 clusters, and for K is equal, there will be 3 clusters. So like this, you see here we are finding, so we will draw 3 clusters of equal size. That is the K means clustering. Now the fourth question, a feature F1 can take certain value A, B, C, D, E and F and represents grade of students from a college. Which of the following statement is true in this case? See, simply it's about grading. We have given grade like 70 to 80%, 80 to 85, 85 to 90, like this, A, B, C, D grades. Now, whether grading like this in statistics, whether this is an example of nominal variable or ordinal variable, or it doesn't belong to any of the category. So whenever we are giving some name, so it's nominal. So it is a nominal variable. Feature F1 is an example of nominal variable because we are giving some A, B, C, D, E and F name. That's the nominal. Now targeted marketing, recommender systems and customer segmentations are applications in targeted marketing, recommender systems and customer segmentation. These all are unsupervised clustering. So these are unsupervised learning, that is clustering. We are doing clustering in targeted marketing, which product shall go where, and recommender systems to recommend which products you shall take, and customer segmentation. These all are from the application itself. The machine does it, like in segmentation always the machine does the segmentation and finds the core groups. So that is of course unsupervised learning always. Now coming to some real stuff, some tough questions let us do. Suppose that in the signal flow graph of the perceptron shown in figure below. So what happens in perceptron? It's a very simple thing. There are different ways to get input. X1, X2, Xn inputs we are getting, and they are multiplied by some weights, and then there is some bias factor to control, and then these weights multiplied by the inputs are summed up here, and then hard limiter is there that limits it. If it's beyond or above that limit, it will be passed. If it's below that limit, it will be stopped here. So that's how neural networks work, perceptron works. Now what the question is saying, that the hard limiter is replaced by the sigmoid non-linearity. That hard limiter is now tan hyperbolic V over 2, where V is the induced local field. The classification decisions made by the perceptron defined as follows. Observation vector X belongs to class C1 if the output is more than threshold. As I told you, it's hard limiter where threshold is a threshold, TH is threshold. Otherwise X belongs to class C2. If it's above a threshold, class C1, below a threshold, class C2. Now the question is, then the decision boundary is so constructed when we have taken this hard limiter tan hyperbolic wave of 2, whether it is line, circle, triangle, hyperplane. What is the decision boundary? So you can stop here and try to solve this question. It's about neural networks, perceptrons. So let us proceed. This is the solution. The output signal is defined by phi with tan hyperbolic v by 2, that's given. So we have put here tan hyperbolic, that replaces v by 2 plus half sigma wixi. Now we have inverted it, so b plus sigma wixi is equal to y dash, where y dash is 2 tan hyperbolic y. So when you solve like this, this comes to be the equation of a hyperplane. So most of the time decision boundaries are hyperplanes only, so this is hyperplane there. Now another a bit difficult question. Consider two one-dimensional Gaussian distributed classes C1 and C2. There are two-dimensional Gaussian distributed classes that have a common variance equal to 1. Their mean values are mu1 is equal to minus 10 and mu2 is equal to plus 10. As there are Gaussians, so they naturally mean and variance will be there. So their mean values are mu1 is equal to minus 10 and mu2 is equal to plus 10. These two classes are essentially linearly separable. Then a classifier that separates these two classes will have values of bias B and weight W. We have to calculate two values, bias and weight. And whether B will be minus 20, W will be 0, or B will be 0, W will be minus 20, B will be plus 10 or W 0, like that you have to calculate. You have understood the problem. Two one-dimensional Gaussian distributed classes C1 and C2. So let us see how it can be solved. From the formula it comes like B is equal to half mu2 transpose C inverse mu2 minus mu1 transpose C inverse mu1. These are the formulas which we have to remember. Then bias comes like this, B is equal to 1 upon 2 sigma square, mu2 square minus mu1 square. Now here mu1, you see mu1 is equal to minus 10, mu2 is equal to plus 10, but their squares will be 100 common. So what will happen? Mu2 square minus mu1 square will be 0. So bias will be 0. While weight will be 1 upon sigma square mu1 minus mu2, 10 minus 10 means it will be plus 20. So 1 upon sigma square, so it will be minus 20. So B is equal to 0, W will be minus 20. So that's the answer. Now the ninth question, see the figure below of a neural network involving a single hidden neuron. This is a very important question. You see they have given, it has been, a loop has been made, there is a single hidden neuron, there is a bias value also. Now the question is whether it works as a XOR gate or AND gate or NOR gate or NAND gate. That's the question which you have to solve through that diagram. So you see, first we can redraw the diagram like this at the same diagram. Now here it's clearly visible that x1 will be plus 1, then it is coming here also. Similarly, there is a bias of minus 1.5, then minus 2 given. So once you will travel through it, you will get two charts like that. The induced local field of neuron 1 is V1 is equal to x1 plus x2 minus 1.5, and you can keep the values and you can make this chart like this. And then will be V2 will be x1 plus x2 minus 2y1 minus 0.5. From this chart you will get this equation, and accordingly we may construct this table. Now in this table if you see y2 will be 0 1 1 0. So that will come, that is the output of a XOR gate. So that's why this is working like an XOR gate. It's very clear. 0 1 1 0. When it's 0, it's 0. When it's 1, it's again 0. And for 0, it's 1, and for 1, it's 1. So like that, 0 0 0 and 1 1 0 and 0 1 1 and 1 0 1, that's output of a XOR gate. So finally it will be an XOR gate. Now the 10th question, the momentum constant alpha. Neural networks questions are very mathematically oriented, but if you will simple logic you apply, it can be done. Like you see this question, the momentum constant alpha is normally assigned a positive value in the range between 0 and 1 alpha. What difference it would make in the behavior of the equation? This is the equation in backpropagation. How the weights are changing is equal to minus, this is the learning rate, minus eta, sigma t is equal to 0 to n alpha to the power n minus t, del del wjit of t, del t. With respect to time t, if alpha were assigned a negative value in the range minus 1 to 0, if alpha here is assigned a negative value, then what will happen? What difference it would make in the behavior of the equation, this equation, how its behavior will change if alpha is assigned a negative value? No difference, or effects will be reversed, or it cannot be assigned a negative value, or none of the above. So here you see the backpropagation algorithm provides an approximation to the trajectory in weight space computed by the method of steepest descent. The smaller we make the learning rate parameter eta, the smaller the changes to the synaptic weights in the network will be from one iteration to the next, and the smoother will be the trajectory in weight space. So what exactly we do with learning rate? What happens? We are trying with learning rate to speed up the process, the learning process. But the problem, what happens, once it speeds up, then weights shift very fast, and due to that the network becomes unstable. So that's why we have to slower the rate sometimes. Now what happens, if the momentum constant alpha is negative, equation becomes alpha is negative. So naturally minus 1 to the power n minus t has been taken because it's negative, then alpha to the power n minus t remains the same. Now this factor is important, this minus 1 to the power n minus t. What it will do? It will start its value oscillating. Here if the derivative, this one del u over del wji has the same algebraic sign on consecutive iterations of the algorithm, the magnitude of the exponentially weighted sum is reduced. But if alternates its algebraic sign, now it will alternate because minus 1 to the power n minus t is there. So as per minus 1, this factor will keep on sometimes it's sign plus then minus, like that. So that alternates its algebraic sign on consecutive iterations, magnitude of the exponentially weighted sum is increased. Thus the effect of then momentum constant alpha is the same as before, except that the effects are reversed compared to the case when alpha is positive. So effects will be reversed is the answer if we will put minus 1 here. Thank you.